Hello everyone. Today I want to introduce our new paper, which is model-based deep learning using monotone non-monotone operator learning. So this is a joint work with Manish John, Jyoti Chand, and myself, and we are from the University of Iowa. So let me start with a quick overview of the current methods. So there are these plug-and-plug methods which use a pre-trained CNN denoiser, which is used in an iterative algorithm, and that gives pretty good reconstructions. The end-to-end unrolling methods, basically instead of using a pre-trained denoiser, they use a denoiser block whose parameters are trained in an end-to-end fashion. So this is done using algorithm unrolling, and here we are just unrolling it to a finite number of iterations that is supported by the GPU. So deep equilibrium models were introduced to minimize the memory demand of the algorithm unrolling based methods. So these methods just use a physical layer and then do forward propagation and backward propagation by using fixed point iterations. So let's look at some of the challenges with these methods. Unrolled methods give really good performance, but they are associated with high memory demand during training, and as a result, most of the methods are restricted to 2 dimensions. So plug-and-play methods and DEQ methods are a little bit better from a memory perspective. However, these methods are guaranteed to converge only when the denoiser is constrained to be a contraction, and this often results in poor performance. Now, the other question is the uniqueness of the fixed point. So these algorithms converge to a fixed point, but depending on the initialization, they may converge to different fixed points, and this might be undesirable. Another question is the sensitivity of these algorithms to input perturbations or the robustness of the method. So you might add a small perturbation in the input that might corrupt the solution quite a bit, and that's undesirable. So the main focus of this work is to introduce a monotone property on the noise predictor. So the noise predictor is basically shown here. So d theta is a denoiser, I minus n theta is basically the denoiser. So n theta is a noise predictor which removes the noise from which estimates the noise from the original image. So the key result is that, or in our work, we constrain n theta to be a monotone operator. That basically says that if you give different inputs, x and y, to this operator, the outputs will be distinct, or in other words, this inner product satisfies this property. So the key result is that once you guarantee this monotone property on the noise predictor, then we can guarantee uniqueness on the fixed point of these algorithms, irrespective of the choice of the forward model. The stationary point is unique irrespective of the initialization. Now we can also show that the algorithm converges to a fixed point provided the step size satisfies this condition, which can be easily satisfied. And finally, the algorithm is robust to input perturbations. So if you make a small perturbation in the input, the output perturbations are bounded by this constant here, which is again another desirable property. So how do we guarantee the operator to be monotone? So our idea is to express the noise predictor as a residual network. So d theta is a denoiser. So you subtract the denoised image from the original image, and that's how you get the noise. Now the key result is that n theta is a monotone operator if the denoiser is a contraction. So how do we enforce it to be by a contraction? So the usual approach is by using spectral normalization of the individual layers. This can guarantee monotone property in a global sense. However, this translates to a CNN with poor performance. So here are some results. So if you just use the ground truth image, we undersample it by a 4-fold mask and reconstruct using sense and model. You get these results. But when you do the MOL-SL algorithm, you get the last column, which is significantly worse in performance than the model algorithm. Now, our idea is not to enforce this constraint over the entire domain. So we just enforce it around the data manifold. So we're basically saying that the monotone property is satisfied in a delta size ball around each training data point. And when we use this property, we can still guarantee all of the desirable properties. For example, the fixed point will be unique within b delta of x, which is that ball. The algorithm converges if we are initializing the algorithm within b delta of x, and it's also robust to input perturbations within b delta of x. So the key result here is that the algorithm converges in that ball, and for that we have to initialize it that ball, and we find that a simple least square initialization is sufficient for guaranteeing that. Now with this, we can improve the performance of the MOL algorithm. So the last column here, it shows the improved performance over the MOL-SN algorithm. We further want to improve the performance. So here we borrow from this clever idea of convex non-convex algorithms. So here the convex non-convex algorithms can use a non-convex prior psi of x. So they basically can choose a non-convex prior provided the total cross function phi of x is convex. So the relaxed constraints on psi of x can often result in improved performance. So motivated by this algorithm, we use a MnM formulation. This is called as monotone non-monotone operator learning. So here we don't constrain n theta as m monotone. So we instead constrain the combination of a Hermitian ax and 1 over lambda n theta of x as local monotone, and all the guarantees follow. So with this, we get almost the same performance as model, and the key result is that this is associated with tenfold or more reduction in memory demand because it doesn't need to do any unrolling, and we also have all the guarantees that we have with model MOL. So here are some results on several training data sets, and I just want to show the improved robustness of this method. So the bottom row is model and the top row is MOL-LR. We see that model offers really good performance when there's no noise, and it's pretty comparable to MOL-LR. However, when we add 10% adversarial noise, the performance of model degrades significantly, whereas MOL-LR algorithm is kind of staying steady, and that's also true with Gaussian noise. So finally, I just want to outline all these methods. So compressive sensing has desirable properties such as convergence guarantee and guaranteed robustness. The MnM-MOL algorithm gives significantly improved performance in terms of image quality. At the same time, it has convergence guarantees, memory demand, lower memory demand, and guaranteed robustness. So the memory demand is much lower than an end-to-end model-based deep learning method.